Today is March 15th, 2023. This is my 25th episode for C++ electricity magnetism with vector calculus classical physics. This is my 6th episode for SYCL. We will masturbate SYCL hierarchical parallel kernel completely. WAP versus subgroup. I learned SYCL by reading Data Parallel C++. This is the only book that we can read about SYCL programming. I'm reading this book the third time. In chapter 4, Expressing Parallelism. If you scroll down, you can find explanation for basic data parallel kernel. Scroll down. Here, you can find explicit ND-range kernels. Scroll down. Here, you can find hierarchical parallel kernels. I read this book twice previously. Now I am reading this book the third time. Now I think I completely understand. When I read this book previously, I could not quite understand all the things. And I found lots of things in this book actually do not work. This explanation, logical range, physical range, did not work. If you scroll down, mapping computation to work items. Here, many-to-one mapping. In the next page, you can find this message. These work distribution patterns are common, and they can be expressed very succinctly when using hierarchical parallelism with a logical range. We expect that future versions of DP's C++ will introduce syntactic sugar to simplify the expression of work distribution in ND-range kernel. This book does not explain work distribution in ND-range kernel, but if you have watched my previous video, you can understand how to create ND-range kernel correctly. I tried the explanation in this book about work distribution pattern, but it did not work quite well. Instead, I applied what I have learned from CUDA. So I applied CUDA technique to SYCL programming. Now, scroll down to Chapter 9, Communication and Synchronization. In this chapter, synchronization via barrier is simple. However, if you scroll down, subgroup is equivalent to WAP in CUDA. I tried to understand this part when I read this book previously. For example, I could not quite understand how to use broadcast. Also, I could not understand how to use collective functions. Broadcast, both, any of, all of. Shuffle, shuffle up, shuffle down. I could not quite understand these things when I read this book previously. However, in this link using CUDA WAP level primitive, double-click this link. I am very confident using CUDA WAP level primitive after reading this documentation. For example, shuffle down think, synchronize data exchange, all think, any think, shuffle up think, shuffle down think. After reading this documentation for synchronized data exchange, then I can understand these things such as shuffle up, shuffle down. My point is, I read books about CUDA programming, then apply the techniques to understand SYCL. Don't miss the best chance to learn SYCL. I assume you have watched my previous videos listed here, from SYCL 1 up to SYCL 5. In our previous episode, we learned ND range parallel kernel. Double-click it. From our previous episode, episode 25, show more source code after filming video. Click it. show in folder, unzip it, rename 25 hierarchical, copy this folder, paste it in your working directory, open up Visual Studio Code, electricity and magnetism. In this folder, we will copy test nd.cpp, paste, rename hierarchical. If you haven't watched my previous episode 24, SYCL 5, please watch it. Otherwise, you may not understand my current session. Now, double-click it. From ND range, we will copy this part. I will arrange side by side. Paste it here. Curly brace, return C, close curly brace. Also, scroll down. You can find binary matrix basic. Copy this function up to function main. Paste it. Now we close this file. Ctrl V. I will not explain this part. Test binary matrix operation. Now open up your command prompt. cd 025 hierarchical ICX CL QSCD C++ 20 EHSC F SYCL hierarchical.cpp oi.exe, hit enter. CLS I. So you should see OK, perfect. Now I will make our problem simpler. Disable this part. Enable this part. We rebuild CLS I. So we generated array A with random numbers. Also array B with random numbers. We will operate array A and array B to create array C. Array C is empty. We are using row 8 times 2 plus 3 or 16 plus 3 equals 8 times 3 plus 5 or 24 plus 9. We will implement this function. Please understand, we are in the local block. In this block, here, auto command group, we capture by L value reference. SYCL handler, it should be L value reference. Command group handler. So we defined command group. Now we use this Q here. Submit command group semicolon. In the command group, we create accessor. We want to access a pop. Then we need keyword template. Get access SYCL access mode read. Don't forget passing our command group handler here. Copy, paste. Now this is B. We want to access this buffer B. In the same manner, C buff. This C buff we will write to this buffer, so it should be right. Now we will create kernel or group kernel. This group kernel is executed per each group. We will capture by value because this group kernel will be executed in parallel. Multiple instances of this group kernel will be instantiated and run in parallel. So we have to capture by value. SYCL group. We are computing matrix. Matrix is two-dimensional. So group semicolon. Now we use command group handler parallel for workgroup. This group kernel will be executed in parallel. Now we specify SYCL range. How many groups? Now scroll down. Our group will have 8 elements. So 2 by 3 groups. Just ignore this part plus 3 plus 5. Just ignore these. We want to execute 2 by 3 groups. So it should be 2 by 3 groups. This is group count. Now in the group kernel we extract int I group. Using this group we can get group ID 0. This is row group. Copy, paste. This is J. Get group ID 1. This is column group. Now we use this group parallel for work item. We pass item kernel. We haven't created item kernel yet. Now scroll down. Our group has 8 elements. 8. Okay. So once again, SYCL range 8, 8. Please remember where this number 8 comes from. 8 comes from here. Okay, now we define item kernel or item kernel. We capture by value because multiple instances of item kernel are executed in parallel. Now SYCL H item YH hierarchical item. We are using two-dimensional matrix item. Don't miss semicolon. Now in this block into I base we multiply 8. 8 comes from here times I group. This I group plus item. This item comes from here. Get logical local ID 0. Copy paste. J, this is J group, it should be 1. Then we access C by passing I base, J base. We call this function. We take this function as parameter. Pass here. We pass A and B like this. Copy, paste, paste. This is A. Now this is B. With this, we run our program. We build CLS I. Now let's see. 7, 4, 28. Why 28? Because we have done multiplication. I will make it addition because it's simpler. CLS I. First notice, okay, perfect. Now 6 plus 5 gives 11. Now what about these? 1, 2, 3, 4, 5. 1, 2, 3 are not computed. Say our matrix is 8 times 2 plus 3. This 3 is 3 rows are not computed. Also 8 times 3 plus 5. This 5. 1, 2, 3, 4, 5 columns are not computed. According to this book. Okay, according to this book, in chapter 4, Hierarchical Parallel Kernels, Mapping computation to work item. In this part, according to the explanation in this book, we are using logical range, physical range. In this code, we are using get logical local ID, get logical local ID. If we are going to use get logical local ID, these things should be processed. However, the 5 columns, 3 rows are not processed, so this documentation is wrong, or I haven't understood correctly. Now let's change it to copy, paste. I will disable it, then I will use get physical local ID, copy, paste. I'm now using get physical local ID. We build again CLS-I. Note, C is all empty. This physical local ID does not work. I will disable it, then re-enable it. Scroll up, I will rename logical. Copy this function name, Control End. It is now logical. Control Home. I will copy up to this point, paste. Scroll up. This is now physical. I will fold it up. We will revisit this function shortly. Scroll up. We restore back to logical ID. We rebuild CLS-I. In our C, 1, 2, 3, 4, 5 columns, 1, 2, 3, 3 rows. Here, 3 rows, 5 columns are not computed at all. So, this documentation, either I did not understand this documentation correctly or is wrong. Now, to make it work, we need to introduce for int I, we call I base. We set I base. I less than rows. I plus equal item get global range 0. For int j, of course it should be this j base here, j less than false, j plus equal this item range, it should be 1. Now I will make block for easier read. We now change it to I, j. So it should be I, j, I, j. we fixed like this. We rebuild CLS I. Perfect. C now works correctly. Let's double check. 2 plus 5, it should be 7. 9 plus 6, it should be 15. It now works perfectly. Now, this is logical. Okay, we move to physical. Please watch very carefully. I will fold up command group. We are submitting command group to our queue. I will expand. Then we are passing group kernel with parallel for work group. Here, the first comes group count, then cut, paste it here. We fixed like this, then remove. This function is physical. Okay, in this function, paste. I will simply copy this like this. Now this is O D. I will copy these. Paste. It should be D matrix. D. 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 Let's see if physical also works. We rebuild CLS I. D. Let's see, in this case, we will fix our physical. Here, we will simply copy from here, copy, paste it here. This is still logical. The remainder is the same. We rebuild CLS I. Matrix D, matrix C, identical. 17, 17, 7, 7, 11, 11, identical. Now we disable logical. Instead, we use physical. We rebuild CLS I. Exactly the same. CD. The same. If we disable it, restore it back. Please note, we are in physical. There is no change. Identical. CLS I. matrix C, matrix D identical. 5, 5, 12, 12. They are identical. However, in the logical, if we use instead physical, let's try it. CLSI. This is D. This is C. This C is wrong. These values are obviously wrong. CLS. We try again. C failed. For example, 2, 8, it should be 10. Then 4, 8, it should be 12, but it is 0. So, in the logical, we pass parallel for work group, range 2, 3. This is group count. For parallel work item, we pass 8 by 8. In this case, we have to disable physical. Instead, we have to use logical. Logical always works. Now, let's see in physical. In physical, whether we use logical or physical, there is no difference. Okay, in the physical, whether we use logical or physical, there is no difference. We rebuild CLSI in both. Now CD identical 5, 5, 5, 5, 4, 4 identical. Before wrap up this session, I will give you some explanation. Here, I will sing a song for you. Grid dim, block dim, block count, thread count. I say block count, thread count. This is my CUDA song. Grid dim represent block count. Block dim represent thread count in a single block. So this is grid dim. This item, this range is grid dim. Here, this is block dim. Block dim is thread count. Group is called block. Also note that here, this 8 is a thread count per block. Y is called block dim. Here, J group is called block index. Here, get physical local ID is thread index. Here, item global range. This is grid dim times block dim in CUDA. This SYCL physical is exactly the same to CUDA kernel.